I'm Tim Ventura, and we're joined today by Doug Finke, the Chief Quantum Analyst for Global Quantum Intelligence, a business intelligence firm focused on emerging quantum computing technologies that helps vendors, governments, and investors to guide business policy and strategic decisions. Doug has a BS in computer engineering from the University of Illinois and a master's in science from MIT, as well as a track record of computer industry executive experience with some of the world's largest computer, semiconductor, and storage companies, including past roles at IBM, Intel, and Western Digital, among others. Doug's foresight about the potential impact of quantum computing in business led him to establish the Quantum Computing Report back in 2015 with the goal of creating the industry's most authoritative source for quantum industry developments. So, Doug, welcome, sir. Thank you so much for joining me today. I want to start out with this role change. So today was the announcement you just took on a new role as the Chief Quantum Analyst for Global Quantum Intelligence. So formally, you were the founder of the Quantum Computing Report. Can you tell me what the new organization will be doing and what brought about the change?
Sure. So I started the Quantum Computing Report in 2015. It was an independent venture. And at that time, quantum wasn't all that big of an industry at that then. So I was able to do it by myself and reporting on the news and analysis, creating databases of what's happening in the quantum industry. But over the past 7 years, the industry has grown tremendously. And there were two other guys who were doing somewhat similar things, although they had some different perspectives. One was David Shaw from Fact-Based Insight, and the other was Andre Koenig from Interference Advisors. So about 6 months ago, we got together. We said, we can't do this on our own, but it's important that we continue working in providing the information that the industry needs. So we've gotten together, and actually today, as we tape this, is our formal announcement of creating this new company, Global Quantum Intelligence, and that will combine our experience and our collective databases. We have over 1,200 web pages. We have gigabytes of data, tens of thousands of data points, and we're going to make this available to our clients in various forms. We'll provide full subscriptions to all of our data. We'll be writing reports. We'll be making market analyses, conducting surveys. The original quantum computing report that I started will remain, although they'll be branded as the Quantum Computing Report by GQI. And
Okay.
we will continue publishing newsletters, letting people know what's happening in the industry, the latest news, as well as helping companies with some of their promotion efforts and advertising efforts. We'll also be providing that. So, our overall mission is to help the quantum industry succeed by really providing the information and advice that they need in order to navigate through these tricky waters of the quantum industry.
Well, you mentioned the rapid pace of change, and it's nothing short of incredible. I mean, so back in December 2020, a group at UTSC, they claimed quantum supremacy with a 76 qubit computer, right? So just about a year later, November 2021, IBM presented Eagle, which had 127 qubits. And just last month, I believe, they unveiled the Osprey system with 433 qubits. And next year, they've got a plan for what they're calling the Condor system with 1,121 qubits. So, looking at these numbers alone, the pace of development here is incredible. I'm also seeing the industry expanding. I'm seeing just so many things moving forward. But I wanted to ask, seeing the scaling of this, are we beginning to see a trend similar to Moore's Law happening? And will innovators be able to maintain this pace of rapid development, do you think?
Yeah, we definitely will. But I do need to point out that quantum industry has one big difference with the classical industry in that not only do you need to improve the number of qubits, you have to improve the quality of few qubits. A measure is called decoherence time and qubit quality. And it's important for the general public to understand that if you talk to a quantum programmer or a quantum scientist, they really would rather have a smaller computer with very good qubit quality than a larger computer with more qubits with poor qubit quality. So you have to increase and expand in both dimensions at once, both in the number of qubits and the quality level of the qubits. But fortunately, that is happening. Um, the technologists are able have made some steady progress in things like decoherence time and gate fidelities, but they absolutely do need to keep it up because just improving on just one dimension just won't make it. But there are a lot of smart people out there. They're pursuing a lot of different technologies and a lot of different approaches in order to do this. I do think they will keep it up. I think there are several tricks that we report upon in the quantum computing report, like networking multiple computers together to create a quantum data center. And that will happen, but it's going to be steady progress. It's not going to be uh, it's not going to be a sudden jump all at once, but year by year, people will continue to improve.
Yeah. Well, and let me circle back and touch on the decoherence. That's one of the challenges of quantum computing. For me, recently, that was a learning lesson as well. I had no idea. I'm used to the traditional computing where, you generate a value, however you generate that value, and it stays until you're done with it. And in quantum computing, it decoheres. It actually loses data over time. And so, if I understand correctly, you basically either have to move that to a traditional machine to store it or use it rapidly before it decays too much. So that's one of the challenges. Another challenge that I'm becoming more aware of is the need for better quantum error correction. That's something that I've been reading about. And I've also heard that even with, over 1,000 qubits coming soon, that for practical applications, it may take machines that are over 1 million qubits before we can really leverage this for real world problem solving. I was wondering, could you tell us a little bit about those challenges?
Yeah, yeah. So let me start quote some numbers. Let's say you have a classical transistor with a classical gate like a NAND gate, and you want to look at how often it makes an error. That's measured in something called fidelity.
Hmm.
A classical computer will have fidelity of something like 99.999999999%. In other words, you could run, those operations for a million years, and maybe once in a million years you'll get an error. So very, very reliable, which is great. In quantum computers today, you're roughly at maybe, depending on the system, anywhere from 98, 99, maybe a little bit above 99%. But that means that if you just string it, let's say in series, 10 or 100 gates, you're gonna get garbage out of the end. So um, you, quantum computer is no good if it gives you the wrong answer. So what the industry is doing is, number one, they're improving the gates. Maybe they can go from 99 to 99% to 99.9% or 99.99%. They'll never be as good as classical computers. And then they are using this concept of error correction, where you basically gang together a whole bunch of qubits. And even though you may have, in some cases, it could be as many as 1,000 what are called physical qubits gang together, and they create what's called a logical qubit.
Yeah.
So even though in the 1,000 qubits you may get 5 or 10 or 20 qubits that have an error in it, because you have so many together, there's some sophisticated algorithms that can still figure out uh, what the logical qubit value is. So when people quote the million figure, that typically would represent a million physical qubits.
Hmm.
And depending on the technology, one ratio that I look at is called the physical to logical ratio. So before I was saying a physical logical ratio of 1,000 to 1, which means that a million qubits, physical qubits, would give you 1,000 logical qubits. And other people with other technologies are looking at something less, maybe 100 to 1 or something like that. And that's, of course, one of the things that the investigators are looking at. They would like to get that number down as low as possible. But the belief is, if you have a machine that has 1,000 logical qubits, which qubits that are almost perfect, that with due to error correction, you won't see the errors. You can do some very serious and very good work to achieve what's called quantum advantage. And in other words, be able to process commercially or scientifically relevant applications that you cannot do on a classical computer. So, but that's where error correction fits in. It allows you to be able to gang together these qubits to come up with something that can process a real world application.
Awesome. Well, thank you so much for sharing that and helping us understand that. That's an area that I've had a lot of confusion about. I know that other people have as well, especially this emerging concept of physical to logical qubits. I literally just learned about that 2 days ago, and it makes a lot of sense. It's just something that, we have to kind of start wrapping our minds around. So I mentioned the IBM news story a few minutes ago, and that one has been, the shockwaves throughout the news world, I guess, just because the rapid pace of development. I wanted to ask, what are some of the most important stories out there that haven't gotten as much press as the big IBM announcement? What are some of your favorites? What are some of the things that you're seeing in the quantum world that you wish more people knew about?
Well, the one thing that I point out about quantum technology in general is that there is a big diversity of different approaches. So there's not a group think type of thing where everyone is doing the same thing, and there could be a fatal flaw in that same thing. Um, I think, as a more general answer to your question, I see a lot of good activity in a lot of the other what are called modalities. In other words, IBM and Google and even Amazon, they're working on something called superconducting qubits,
Hmm.
which are good. They're certainly made a lot of progress, but there are other modalities like ion traps, photonics. Um, Cold neutral atoms, NV diamonds, various other things. And at this stage, the industry is so immature. I think it's good that we have so many different approaches, because if one doesn't work, then one of the others. So I think over the past year, I think the thing that's really I think is the big story is that a lot of these other modalities have matured and they're now becoming available to customers. For example, Amazon over the past few months has added a machine from a company called Quera, which does neutral atoms. And they have an interesting feature called analog quantum computing, where it's perhaps for some problems, particularly computational chemistry problems, it can possibly be more effective with fewer qubits using this analog mode. Company in France called Pascal also has a similar thing, but there are companies doing photonics. A company called Xanadu, for example, is offering a photonic-based computer, and other companies are joining it. So, not sure, at least in the computing side of things, I would point to any one specific thing. I just think it's all these other developments, working together. Now, I would also say that quantum does have three branches. There's, I consider it to have three branches. There's quantum computing, quantum communications, and quantum sensing.
Hmm.
And we're also seeing a lot of progress in those other two areas too. In quantum communications, what we're seeing is a lot of, I call them test bed networks, being springing up, anywhere from London to Canada, the Chicago area, New York City, Long Island, California, and people are creating, I call it small quantum internet that will allow you to send out qubits from one place to the other. Um, the, the problem that these networks have right now, the big technical problem, is that they don't do long distances. So you can't go from like New York to California because of the loss in the fiber optic cable. You just sort of lose the
Oh,
qubits.
okay.
But there is research in terms of something called quantum repeaters and quantum memories that will enable that. So I've seen some research. I think some of the very first quantum memories have been sold over the past year. So I think that's a very significant event. And I should mention quantum sensors too, because quantum sensors probably an area that will also have some good impact, but they don't get as much press. But uh, for example, the Department of Defense is looking at building and having navigation systems that don't depend on GPS, what they call GPS denied environments, that would use quantum technology, very accurate quantum clocks, and other sensors in order for an airplane or a ship to know where it is, even if the satellites, the GPS satellites, aren't there. As well as things like quantum magnetometers to sense the magnetic field, which could be used for things like mining that might be able to figure out where an ore deposit is or something like that. So there's a lot of different things that are happening, and I think it's more than just in the quantum computing market.
Absolutely. And one of the things that I've been seeing, especially on LinkedIn, is a lot more people as well working on, I guess you would say, the emerging industry side of it, right? Especially in terms of programming. I keep hearing references to like Python, Qiskit, Ocean, Q Sharp, and the Circ languages. So, it looks like people are working on the programming side, building initial software applications. There are also simulators out there that people can use. And if I understand correctly, you can actually rent time on like an IBM quantum computer online, right? You can actually schedule time on some of these early machines using the web. So it sounds like those things are moving forward. Could you tell me a little bit about what you see in terms of the industry, maybe the certifications, programming, things along those lines?
Yeah, on the software side of things, there's two trends that I would point out. As you mentioned, there are a number of different quantum programming languages. Um, but one trend we've seen over the past couple years is something called hardware agnostic. I was just saying a minute ago that there's so many different quantum systems out there, and the good news is if you're an end user, you may not know which system might be the best for your application. And in fact, it might differ. Some applications might favor one technology and other applications might favor a different one. But what the software, what we call them SDKs, software development kits, are doing is they're saying, look, you can write a quantum program at a high level, something like Qiskit level, and then we can compile it to different machines by having different backends. So there's a lot of work in creating different compilers for the different backends, as well as optimization. Optimization, of course, has been a long process in the classical computing industry. Quantum is doing that now too. I think it's actually more complicated to optimize a program for a quantum computer because of some of the errors I was talking about before. There's a lot of different things you can do, for example, to reduce the depth of the circuit and those types of things that will give you a more accurate answer. But that's sort of at the end of the software tool chain. Um, at the upper level, I think the other thing I'm excited about is that people are working on creating software that allows you to program at a more abstract level. The problem is you have a lot of people who are end users and um, knowledgeable about their own particular field, like logistics or chemistry or those types of things. And the quantum industry will never really get anywhere if those people have to program at very low levels at the individual gate levels, which is what they've had to do previously. But there are a number of companies that are saying we're going to put together very high level quantum, high level programming environments. I call it quantum programming for people who don't want to learn quantum. So, there's one company, for example, Multiverse in Spain, that allows you to program a financial problem in a spreadsheet. You take an Excel spreadsheet, and let's say you're doing portfolio analysis. You can put, the key parameters in that spreadsheet, and then their program will take that and convert that to a quantum program. There's other companies that are certainly putting together libraries and allow you to program at a high level. And that, I think there's a lot of innovation. I think it's very, very important that we continue with those efforts because someone pointed out that if I had a million qubit quantum computer today, people probably wouldn't know what to do with it because to be able to program a million qubits, at the gate by gate level, it's just not feasible for any human being to do that. So higher level programming at the front end, and then hardware agnostic, and as well as very optimal compilers at the back end are key things on the software side.
Yeah, well, and thank you. It is, I think it's very important to point out that this isn't the same as the emergence of the computer the first time around, because we're able to benefit from this existing industry, right? And it seems like, and this has just been my impression, but it seems like the industry is getting a head start on it, as you've mentioned, with the emergence of high-level programming languages. And so when the hardware is ready, the software and the infrastructure and the ability to use it should be ready as well, right? As opposed to, again, more traditional computing where, the hardware and the software were both kind of racing forward in lockstep. So that's the impression I get, at least. Now, I did want to ask about the business sector in general. Again, there's so much moving forward in this. And I know that you track industry funding, financing, and partnerships. What can you tell me about this area at the moment? And does it seem like we're starting to enter a tech bubble in terms of funding, or is that something that may occur down the road?
Well, let me start with a quote that I give to people. I get often asked, will there be a quantum winter? And what I tell people is, no, I do not think there's going to be a quantum winter, but I think some people are going to get frostbite. So, like any new technology, there is a lot of risk. Some efforts will fail, but some will succeed. But looking at the funding side of things, let's start with the government. There's a lot of government support worldwide for quantum computing. Uh, we all know about the U.S. National Quantum Initiative Act, but countries worldwide have very similar things. And the interesting thing is, many of the countries in Europe and elsewhere are saying, look, we don't want the US to dominate quantum computing in the same way that they dominated some of the early classical computing. So they're putting as much money, if not more, into that funding. And the thing about government funding is that it's long term. It's not one of these things where people get hot on it and they'll make an investment for a year and then things don't work out, they'll go away. Government is very stable. So that's one of the reasons I say there's not going to be a quantum winter. There definitely has been, an increase in terms of the venture capital funding for for quantum. I would say that as the industry matures, the bar is getting higher for companies in order to be able to secure that. They do have to show results, but some of these companies are indeed securing results. But there are a few companies that were not able to get funding and have actually gone away already. So we will see, continued steady progress, continued funding, but I will caution everyone that if you do make an investment in this area, it's a long-term investment. The revenues and the profits are still probably 10 years away. Uh, and it's not something that, like crypto was last year, where you could buy something and turn around in 6 months and double or triple or 10 times your money. That's not going to happen in quantum because there's still a lot of technical work that needs to happen for it to happen. So you need patience in order to be successful as a quantum investor.
Ah, wonderful. Well, Doug, let me thank you so much for your time today. And let me close by asking, what do you see coming next for quantum computing in the short term? And what's coming in the near future for your work with global quantum intelligence?
So definitely believe that over the next couple of years, 2023 and 2024, we will see continued announcements and enhancements with more qubits, better qubits, more quantum networks, those types of things. Um, I think you may start seeing the very first, I'll call it trickle of real world applications that are using quantum on a production basis. There is a term that's called NISQ, NISQ, near term intermediate scale quantum, that is not error corrected, but people are trying to be able to come up with useful applications. And you may see a handful of them, let's say in the next 2 to 5 years, before we have fully error corrected quantum computers that are able to do useful things with the quantum
Mm,
computers they have at that time. I've told people that the human race is very ingenious, and even though a lot of, quite frankly, a lot of the experts think that nothing can be done, I think there's going to be some innovations there that people didn't expect. So we will see that, gradually. Again, at, let's say the 5 to 10 year mark, we'll start seeing the hardware itself move from this NISQ unerror corrected to fault tolerant with error correction. And you may see there's some graduation there. People are working on things called error mitigation, for example. Um, but it is a very complicated landscape. Um, if you are a participant, either a provider of quantum services or a potential user of quantum services or an investor in quantum services, um, it's quite frankly, it's going to be really hard. We track over 600 companies that are in this space at this point. So for global quantum intelligence, we are going to help people navigate through that so they can understand what's happening to clear away the fog to some extent so that people can plan their strategies and their implementations and their investments um, in order to be most successful. And that's our mission, and we'll be doing that for the next several years.
wonderful. Well, Doug, I will definitely put links into Global Quantum Intelligence as well as the Forward Quantum Computing Report. I will put those in the podcast notes as well. And let me thank you again so much for your time today, sir.
Well, you're welcome, Tin. I really enjoyed talking with you, and looking forward perhaps to talking with you again sometime.
Absolutely. Have a wonderful day.
Okay, thanks. Bye.